Hi everyone. Uh, for the course project, I that's basically talking about features such as temperature, pressure, humidity, and exhaust vacuum to predict the energy output. Uh, I'll go through all the key components, key questions that we have to answer as part of the course project. So, starting from the first one, I used linear regression for this particular problem to predict what would the output look like using all of these features. And to get a sense of how important all these features are in our prediction, I just took out the entire data set and I created this model based off the data set here. And you would notice that our R square is 0.93, very close to 1 to 1, which means the the 93% of variance in our output prediction can be attributed to these factors, which for me is fairly impressive, how close to 1 we are. Now, with respect to how significant each of these values are in the prediction, if you look at the p-value here for 80, so temperature, vacuum, pressure, and humidity, all of them are less than 0.05. So they all play a significant role. So the modeling that I did, I basically did two kind of I created two kind of models. One where I basically used all the four features to get to a prediction, and in other cases I removed one, and I'll talk about that. With respect to the approach that I took with respect to how do I train the data and then how do I validate my prediction, I'll quickly get to that. So you notice that I have here, I took 90% of the data for training the model and then 10% of the data to testing and validating the model. And so you have 8,611 observations that I'm going to use for the model building, and then we have around 957 observations that I am going to use for validating the model. So using this model, I created this output. As you can see, I used all the attributes, all the features. And in this case, for the reduced data set, we can see the vis-a-vis when we take the entire data set, the R square here and the R square here, there isn't much change. It's pretty actually uh, quite same actually. Uh, the difference is unnoticeable really and insignificant. And so using this, the prediction is and the model is performing really well. And when I am testing it, so for example, you can see that this is my validation data, this is my actual value, this is the predicted value. It's performing quite well. You can see across many, the prediction is quite consistently close to the actual observation. In model 2, where I actually again I kept the same sort of data slicing for training data and training the model and validating the model. And in this case, what I did, I removed one of the features. So the one that you would see I removed is here your valve pressure, vacuum pressure. So I removed that and then I ran the model. Now in this case, you would notice that there is a slight dip in the model's performance from 0.93 to 0.92, but it's still behaving reasonably well. And performance is still fairly solid. The p-values are all significant, more than 0.01, 0.05. And in this case, you can see the predictions. It's again, there's a quite nice performance here as well. With respect to when I start comparing which model 1, where I had all the key variables, key features, and in model 2, where I actually removed the vacuum pressure one, and then I compared, and so this is your actual, this is the prediction for model 1, this is the residual for model 1, this is the residual for model 2. You notice that it's not very far off. And so if I sum all the residual values, you can see the number here is negative 80. In this case, this is negative 94. So one can argue that model 1, where you have not removed, you have kept all the features, is behaving better. So yeah, thanks for attention, everyone.